It's rare that a single project answers all questions. As scientists, we sometimes need to be able to connect information. This can include connecting information over temporal scales, where we might be interested in the processes that have happened in the past that allow us to see what we're seeing today, or these can be connections between individual systems and broader spatial scales. I want to talk today a little bit about how we can connect to some of this broader scale information. We're familiar with the detailed knowledge that we gain from science occurring within individual systems. These are the processes, or the places where we get information about processes and detailed, deep understanding about systems. At the same time, limnology has a rich history of incorporating surveys to get their information about systems at broad spatial scales. We can think back to the early days of Burge and Judet, where they used both information about intense information about individual systems and conducted surveys across regions to get some information about variability at that scale as well. Then and now, there can be strength in leveraging information from individual systems and across broad spatial scales to aid in discovery. There are always questions about how we get there and once we get there, how we can connect to this information. And that's what I want to talk about today. In a theoretical context, the connection between spatial scales is quite clear and seems like it might be easy to achieve. We can take this single alligator-infested lake in Florida to start to explore this idea. They didn't know that I didn't like alligators when I went to this lake with them. But within a single system, we have the opportunity to develop deep understanding about the processes that might be occurring. We have an opportunity to learn about the biological assemblages or community interactions within that system. We can focus on chemical processes occurring within a system, physical characteristics of that system, and how we as humans interact with each of those aspects, either individually or collectively. Sometimes we might want to take information from those single systems or the processes that we're looking at in those single systems and understand if we see patterns across the landscape that reflect the processes in that single system. To do that, we can start to move towards a regional network where we understand that systems are connected through the landscape that they occur in. And this is still a tractable unit for some folks to start to address questions. We, of course, understand that that single region lies within a context of the broader boundaries, either ecological boundaries or political boundaries. And both of those are displayed in this map of the US. Dots of a similar color reflect aggregated ecological regions where systems are thought to have some ecological characteristics in common. And then we have political boundaries. And the important part about this, from where I sit, is that many of the environmental management decisions are made at those political boundaries, which sometimes expands beyond where we have scientific information. And so we need to know when it's possible for us to develop generalizations to these broader scales, and how we get there can be important. So in a theoretical context, it might be easy, and it seems like maybe you just compile all of that data from single systems, and it's additive, and you put them in a database, and voila. But in reality, that is not usually the experience that people have. Many aquatic scientists are turning to sort of broad-scale information to understand the impacts of processes occurring either locally or at broad scales, or to understand temporal differences. And so there are exercises where people are putting together broad data sets and working together to pull together vast amounts of information. And we're learning a lot of interesting information about how systems work and about some of the patterns that might be occurring both within sort of broad regional areas or globally. And in addition to the important research and information that we're gaining from these systems, we're also starting to learn some of the challenges that people have when they're pulling together these broad spatial data sets. If data is available and ready to be consumed. There are questions about which resources are sampled, which measures are recorded within those ecosystems, and whether that data is compatible at all. I would like to add an additional consideration to the considerations that have already been detailed in the literature to the limnological community. That's one of sample design. So of course, sampling design is something that we consider when we're developing a research project, when we're getting ready to go out in the field ourselves. I posit that this can also be important as we're starting to pull together information to address questions at broad spatial scales. So I'm thinking of two buckets of sample design. One is traditional targeted sampling design, and this is where we go out and identify systems based on characteristics that are important for our question. In this case, it might be because it has a characteristic of interest, like a fish population of interest, or it might be it might lie along a gradient of interest, or it might be because it's co-located with our field station and therefore reasonable to sample. Another bucket of sampling design might be something like statistically representative probability designs. And in those designs, we're targeting a population, or we're targeting sample sites that reflect a population so that we can talk about a broader set of sites or of characteristics across those systems. Steve Paulson and colleagues illustrate an example of the importance of sampling design using coho salmon in coastal Oregon. Coho salmon are an important cultural and recreational and food resource, and there's a lot of investment into their populations and maintaining their environments. In the 1950s, some of the scientists within the state agency in Oregon were asked to develop a spawning study for salmon. And so they went out and identified 50 streams where they had salmon, and then they would count the spawning salmon. And then that became a long-term data set for them, where they were looking at how salmon populations over time. This information was then used to extrapolate to the 4,700 miles of streams in Oregon that are thought to support salmon populations. This is a robust long-term data set. They've been going out to those 50 sites for quite some time. In the 1980s, the question or the objectives started to shift, where people not only wanted to use the information to understand populations within those streams, but they also wanted to use that information to predict future salmon stocks in the ocean. And then that information they were hoping to use to set harvest limits. Because the nature of the objectives changed a little bit, some of the scientists within the state agency became a little concerned about some of the assumptions of the sites that they sampled. And so they set up a side-by-side probability sampling approach. And those results are shown here. And there are a couple of things to note here. First is that the overall pattern is somewhat the same. And so they were getting sort of the trajectory the same. But there's a 3 to 5-fold difference between what they were getting between the traditional design and the probability design. And this makes sense. When they were tasked with coming up with salmon spawning study, they went to find streams where they would find salmon, because that makes life a little bit easier. But those sample sites turned out to be much more productive than the other sites that they might have selected if they had known that the objective was to talk about salmon stocks in the ocean and to predict out for that information. And so, of course, we think about sampling design when we are coming up with our own studies, but it's also important for us to consider whether there might be unintentional biases as we're pulling together data. Sometimes it won't matter for your question, but other times it might be important. And so it's just another consideration that we should include. So fresh off the heels of that study, Steve Paulson and other people at EPA were starting to get asked a lot of questions about the character of waters in the US. And they thought about some of the concerns that folks had about representativeness of sample sites, and some of the difficulty of working with existing data sets. And we work in partnership for this effort with our state partners and our tribal nations. And the state partners and tribal nations tend to have really deep understanding of some of the waters that they have within their boundaries. But pulling together that information would mean pulling together 50 different data sets that might measure different things. And that became a challenge that this group didn't want to take on when we needed to do something periodically to look at temporal trends. So they started a new synoptic sampling program called the National Aquatic Resource Surveys. The broad objective for this project is to assess the biological, chemical, and physical and recreational condition of aquatic resources across the U.S. at regional and sort of national scales. I'm going to focus on lakes, not just because they're the best, but that's what I'm most familiar with. But I do want to note that there are equal efforts to collect information from rivers and streams, coastal ecosystems, and wetlands. And so if there's interest in pulling together some of these data sets, that's an opportunity. Each of these projects includes a stratified randomized sample design so that we can talk about population. There's a standardized field and lab protocol so that we can escape some of the challenges that you all have been dealing with in compiling data. There's consistent quality assurance because we're EPA, and there's a consistent data management program. We also interpret the data to make it available to policymakers who might be from very different backgrounds, so we provide some context for data interpretation. So in the National Lakes Assessment, we're interested in talking about lakes across the country. This is a map that was put together by Ryan Hill and Mark Weber and others, where they're looking at lakes greater than 4 hectare, equal to or greater than 4 hectare, and it would be any water body classified as a lake, pond, or reservoir across the conterminous U.S. There are over 380,000 of these water bodies across the U.S., and I made the wise decision to go down to 1 hectare lakes in the 2012 assessment. So there are more water bodies that we're trying to describe across the nation. Given that we have neither the inclination, time, budget to sample all of these systems as a regular part of our effort, so instead we use a statistical sampling design where we identify a tractable number of sites that our field crews can visit within a 4-month period. For us, that's 1,000 sites distributed across the U.S. This is a stratified randomized design where we're stratified by lake size, so we're not just getting small lakes, and ecoregion, so we're getting distribution of lakes across the country. Because of the design that we use, we're able to take the information from these 1,000 sampled sites and then extrapolate back to the broader population. So when I say population of lakes, I'm usually talking about either somewhere between 50,000 and 100,000 lakes across the U.S. We take this information and develop broad-scale statistics as you would get from, that we're more familiar with in sort of the social sciences realm or in politics, for example. So we could say that from the 2012 assessment that 40% of lakes in the conterminous U.S. have signs of phosphorus pollution. We can also break this down in terms of regions. And so in this figure here, we have the 9 ecological regions that I talked about before. And in that first panel, we have the proportion, each bar represents the proportion of lakes with phosphorus pollution in that ecoregion. The gray bar shows the national estimate for population, and that's bounded by the 95% confidence intervals. And then that second panel shows spark lines, which just gives people who are only kind of interested in this data a quick indication of change. So it tells you whether lakes are staying the same increasing in their phosphorus pollution or decreasing in their prevalence of phosphorus pollution between survey periods. And then that final panel gives you information about the magnitude of change between assessments. So what we can see from this is some of the differences across the US and some of the variability that we start to find. So in the northern plains, for example, we can say that we estimate that 80% of the lakes have signs of phosphorus pollution, which is significantly higher than what we see nationally. We can compare that with the western mountains, where there are significantly fewer lakes than in the nation and certainly than in the northern plains, where we're seeing signs of phosphorus pollution. We use regionally relevant observations to come up with these estimates, and so that's 80% of lakes compared to the best available lakes that we're able to find in sort of the northern plains. So it's what we think of, what they call in my management world as achievable targets. Oh, it wouldn't be like me to not point out that all of the information that we provide, the statistics we provide, and the data underlying these plots, not just the population data, but also the data from each of the sampled sites, is available at our website. You can also find data on wetlands, rivers and streams, and coastal areas there, and it's available for you to use. Please use it. So we come up with these statistics about water quality characteristics across the US, and that's our primary deliverable. But what a group of us are interested in is sort of how else we can use that information. And today I want to talk about how we can leverage some of this broad population scale data for increased understanding about water bodies and sort of make that connection between different scales. So I'll start with nutrients. We know that some of the activities that occur on the landscape can impact the delivery of nutrients to ecosystems. And we are familiar with the idea that there are consequences to nutrient addition in freshwater bodies. And that was demonstrated nicely in Lake 226 from the ELA here in Canada. For this project, we were particularly interested in two different populations. One of lakes, which are in this exercise were greater than 4 hectare. We had 2 survey periods, one between 2007 and the other 2012, to focus on for this question. In each of those populations, we had 1,000 sampling events, and then there are about 40%, so 400 sites that are sampled in both surveys. We call those resample sites. The second population that we were interested in is in wadable streams, and there are 3 sampling periods for that survey. One between 2000 and 2004, the second between 2008 2009, and then the third 2013 to 2014. These have 2 years because they collect information from 2,000 sites for each of their assessments. And there are about 25 to 30% of the sites that are resampled in that project. So we can take this population level data and look at change across populations. And so when we do that with wadable streams, we can look at the median, and we see that in the first survey in 2000 that ended in 2004, we had a median concentration of phosphorus of 26. That went up to 48 in the second survey, and then up to 56 in the third survey. The same kind of pattern was observed in lakes, where it went from 20 up to 37 in the second survey. Because there's population data, we can also look at the distributions, and we see that the distribution is tightening a little bit around those estimates for each survey. I recognize that I've become a little desensitized to this because in reality, the median concentration is doubling, and I just look at it and think, oh, it's going up. But what we're seeing is a pretty significant or a pretty dramatic change over time that's occurring across populations in the US. And what's compelling about it to us is that it's occurring in both wadable streams and in lakes. And so it caused us to take pause and ask some additional questions. we might expect to see changes in nutrient concentrations in some of our more impacted lakes that show typical signs of nutrient pollution. But we also were interested in what might be happening at some of our low nutrient oligotrophic systems. And so we decided to also take a look at that. And so this plot's a little bit different, where we're really focused on the population of water bodies that we would classify as oligotrophic. And in this case, we're using 10 micrograms per liter as oligotrophic. In the first assessment in wadable streams, there are about 25% of the stream miles that we would have classified as oligotrophic in the first survey. That went down to about 10% in the second survey, and then down to about 2% in the third. The same kind of pattern was observed in lakes, where we went from about 25% and then down to about 7% in the second survey. And so in this sense, we are seeing a decline or decrease in the proportion of water bodies that we would classify as oligotrophic, which caused us to ask a variety of questions about what might be going on. And so we can go from this broad-scale population information and start to delve in a little deeper to see whether patterns are occurring regionally or locally, or if they're widespread in nature. So to do that, we used the same data set and broke the information down into a site-level analysis where we were really focused on those resample sites between assessments. We applied very stringent benchmarks along that data set for resampled sites so that we were able to identify the least disturbed catchments that were sampled in each survey. And then we plotted them to see if there were sort of local characteristics or if this was widespread change. And the color here represents the amount of change in phosphorus. What we see here is that there are widespread changes. We also see that there are not sites in the middle of the country. We do sample sites in the middle of the country. It's just that they don't happen to pass these stringent screens. But we're seeing changes of the same magnitude both in Southern California and in northern Maine. And so this is a large-scale change and one that might be operating in remote, undeveloped areas. We can use this information to start to identify hypotheses. And so we started that process, but certainly as one develops these hypotheses, we would then want to connect to some systems, to some experiments or other work that might be occurring in individual systems so that folks can look at mechanisms. But just to go through a couple of the hypotheses that we ran through to start to narrow them down, we of course looked within and thought maybe it was our data quality. Fortunately, we had one lab that analyzed almost all of our samples, and there were not significant changes in our methods. And we have this extensive quality assurance that applies both to our lab and to our data sets. So we could eliminate that hypothesis. Then we thought a little bit about the classics, but that wasn't congruent with the changes that we were seeing in these least disturbed systems. Changes in hydrology, we looked within the basins to look for changes in hydrology, and we didn't see evidence of that. And that leads us to just some hypotheses that other folks can test and that they're looking into. Things about whether there's increased dust or dry deposition that might be increasing phosphorus concentrations in some of these systems. But in this way, we're able to connect this phosphorus data that occurs at broad population scales to some hypotheses that then can be tested on sort of a smaller scale and in individual systems. And that's kind of the nice circle of how science could work with this type of population data. A second example that I'll run through quickly is that of habitat. Our fabulous field crews take detailed information about riparian characteristics and littoral characteristics at 10 stations around each lake. And then we summarize that information as a part of our reports. We have one of the measures we call Shoreline Habitat, but it's really referring to riparian vegetation complexity and cover. And in the first survey of lakes, we found that 36% of the population of lakes had this riparian cover in a most disturbed condition. And that this most disturbed condition had an impact on the characteristics that we see within a lake. And in this case, lakes that had had shorelines in most disturbed condition were 3 times as likely to have degraded biological condition as well. It's not that the results excited people, but there's potential here to take these results and to connect them to individuals. Because when you're talking about riparian habitat, we can develop communication materials that go right to people who have the ability to change their own behaviors and see potentially some impacts within the lakes that they enjoy. And so that's what we did. There was a communications campaign that was targeted to lake owners and realtors, and that was a success that some folks are still using. I just talked to someone last week about this. We can take another example from Vermont, which is in the Northern Appalachians ecoregion, which is highlighted here in black. Vermont had a couple of things happening at once. Between 2005 and 2008, they were really interested in the impact of riparian development on littoral habitats. And so they set out to do a study within their state where they identified 40 lakes and looked at the differences of riparian development and the impact on littoral areas. They detailed this work in a paper that they titled "Examining Shorelines Littorally," which I love. And they found differences, as you might expect, and documented them so that they could better understand some of the impacts of riparian development on their water bodies. In 2007, Vermont also participated in the National Lakes Assessment, and they added sites so that they were able to develop a population-level analysis within their state boundaries. The results that related most to their riparian disturbance metric we call Lakeshore Disturbance, and it's just an observation of human disturbance within the water or within the riparian area. And they observed in their state data set that this lakeshore disturbance was the most widespread stressor around Vermont, which surprised them to some degree. Not only was it the most widespread stressor in Vermont, it was also more widespread in Vermont than in their neighboring states in the Northern Appalachian ecoregion. And also, they were in a more disturbed state in Vermont than they were nationally. Sometimes comparing oneself to others can spur change. In Vermont, the scientists within the state agency were able to pull together these different lines of evidence using both this broad-scale population information along with some of their more detailed information from specific sites within their state. And they started to use this information to communicate to their stakeholders, including to their legislature. And in 2014, they were able to push forward the Vermont Shoreline Protection Act, which was developed to guide development within 75 meters of the mean water level around lakes. So this act is intended to prevent degradation of lake water quality, preserve habitat and natural stability of shorelines, and to maintain the economic benefit of lakes within Vermont. So they had an opportunity in this case to combine some of this broad-scale population level information and enact it with their information to compel change. So those are two examples. Neither of those examples addresses the question that I get most frequently. And I have to admit that when I hear this question coming, my head fills with a song from an artist, Janet Jackson. And it asks, "What have you done for me lately?" And the discussion goes something like this. Great, you have broad-scale population level information. What does that have to do with me? I hear that question from folks in the research community. I hear it from folks who are lake association owners or lake association members, from individual people who like a specific lake. and from resource managers who are particularly invested in a specific system. And it's an important question because individual systems is the scale at which most of us interact with the landscape. And so it's important, if we want to continue to communicate about this information, that we start to develop this connection. And so I've started working with someone a couple of months ago about different ways that we can help to bridge this gap a little bit. This is Baker Lake, as you might have guessed. And we can use lovely Baker Lake to start to address this question. So Baker Lake is in Washington State, which is in the Western Mountain ecoregion of the US, which is highlighted here in black. Baker Lake, for this example, could have been sampled as a part of the national effort, or it doesn't have to be. As long as you have a little bit of information about the system, we can help develop that connection. So in this example, the way that I'm thinking about it now, we can ask, how does this lake compare to the population of lakes from the NLA? So if we have, let's say, phosphorus information from Baker Lake, and we do, and it was 15 micrograms per liter for phosphorus, we can overlay that with the national population. And this is the weighted phosphorus values observed across the population of lakes. And in this case, this is 2012 data, so it's lakes greater than 1 hectare. And we can see that nationally, Baker Lake is in the 17th percentile of lakes. So this is like an education statistic where 17% of lakes have lower phosphorus than Baker Lake, and 83% of lakes have phosphorus higher than Baker Lake. For people who are interested in comparing themselves to something, this option might work. And also, if you're in a research community and you're interested in nutrient enrichment questions, it might help to know sort of where you lie along that gradient, just so that you can have some additional context for how you think about your system and the processes you might observe. As I mentioned, Baker Lake is in the Western Mountain ecoregion, and we know that that ecoregion tends to have lower phosphorus values and lower levels of phosphorus pollution. So we can break this information apart and start to look at the population within the Western Mountain ecoregion as a comparison. And there we find that Baker Lake is in the 29th percentile of lakes. Or if there are other characteristics of the system that you might be interested in, this is an example with size class, where we know that Baker Lake would be classified as one of our larger lakes because it's greater than 50 hectare, and in that case, it's in the 24th percentile. So we have an opportunity, when we want, to be able to connect individual systems to this context of the larger population. And this might be able to help us start to bridge that gap between these broad-scale populations and individual systems. So I've walked through 3 examples relatively quickly about using population information. In one example, we can use population information to explore patterns across the landscape and then develop hypotheses that we might investigate later in single systems. In a second example, we can use population information with additional data to help better understand our systems within an area, and in some cases, to compel change. And then finally, we can use population level information to give us context about a single system that we might be particularly interested in. Before I go, I'd like to just talk about another sort of connection that we have through this project, and that's related to the connection of the people who carry it off. There's a broad group of people that are involved with being able to develop a new population estimate every 5 years. There's a planning process that involves EPA, states, and tribal nations, where we go back and reflect on what's been observed in the past, new information coming out of systems, new ways of new measures that we might want to include in the assessment. That information moves forward to an implementation team, I'll call them, where we work on the logistics of getting equipment to people and getting them out to sites and getting them trained in the methods that we want to use nationally. And then we have about 90 field crews that descend upon the United States to sample those 1,000 sampling events within that 4-month window, and they finish on time, which is amazing. And because we're selecting sites from maps, they're not always reasonable. So they don't always know what they're going to encounter when they go out to those sites. Sometimes everything's great, other times there are challenges involved. After they collect that information, it all comes back, and we do sample processing. Once the samples are processed, that information comes into an information management team, which is really a group of maybe 3 people. That information management team prepares it for the data analysts, and then we take that information and provide context, and then develop communication materials, and then we have approximately 24 hours to rest, and then we start over again. So it's a fast process that occurs, but the population level data that we have wouldn't be possible without this network of people. And that's just within this single project. There are other networks that are occurring across the country and across the globe. And so when we have opportunities to connect to other projects like the HABs, the Harmful Algal Bloom project occurring in the EU, that's very exciting. Or if we connect to the Lake Pulse project occurring here in Canada, where they're doing similar types of work on many systems here. That fosters another set of resources where we can start to look at even broader scales in a similar way, and hopefully we'll be able to connect that information with you all, some of the people who might use this information, and to our broader questions. And I'll just close by saying that with multiple environmental impacts, connecting information in local and broad scales is sometimes necessary. Our challenges don't seem to be diminishing collectively. And so sometimes it's important for us to know which resources we can leverage and how we can leverage them. And I'm hopeful that this gave some insight into how we might be able to use population level information to address some questions. Thank you.